Hi, we're back with binomial distributions. How happy are you? This is great, isn't it? We've got the third piece coming up here. And I want to talk a little bit now about actually how you would calculate and get a sense for what's usual to happen and what's unusual as far as discrete distributions go. So just to step back for a second, and we've had this little bar scenario come up where there's 2.5% in each end and 95% in the middle, and this is usual UAL. This is unusual out here on the ends. And remember that on slide 6 that you'll be seeing up online, the maximum values and the minimum values are the mean, or X bar, and it's also denoted by the symbol mu, which you'll see in the text and you'll see in other literature. But X, the mean, equals the average, X bar. It's also called mu, and it's up on your slide as mu, plus 2 standard deviations. And on your slide it's plus 2 lowercase sigma. So mu plus 2 lowercase sigma means the same as X bar plus 2 standard deviations. And that's the maximum value up on top. So we take this average, whatever it might be, plus 2 standard deviations, and then the mean minus 2 standard deviations will give us this lower extreme. So I just wanted to set that up on slide 6, that that's what really sets our extremes. Now let's take a look on slide 7 at a probability histogram. And on that slide you'll see a bar chart with probabilities identified on top of each bar. Now I've labeled up on top on that particular chart that the underlying probability is 80%. Remember when we did the patients just a little earlier, where it was 50% that they'd be admitted on time or not, or flipping a coin was 50%? Well, in this one we're talking about a Mexican-American population, and the underlying population percentage is 80%. So this distribution represents a distribution with an 80% underlying population, and it represents a number of trials of 12. So just keep that in mind as we move along. One thing that comes back to me, and that distribution looks like this, and there's a 10 under the tallest bar, 11, 12, 9, 8, 7, and this is the juror selection that is on that particular chart. This is kind of fun. You can do this with your neighbors, friends. You have anybody over for a party. You get your probability distribution up on the wall, and think of it as plywood. Okay, so let's say we cut this out. We take our little saber saw and we're cutting. In fact, I hear a saber saw outside right now. I bet it's somebody cutting a histogram up for all the fellows out in the yard. Here we go. We're cutting up this this plywood distribution, and you can see I can get this out, and it has a physical weight, has a physical distribution. I can pull that right out of the board here, and if I were to balance my finger under where the balance point would be, you know, it wouldn't balance if I was over here. It would fall this way. It would still fall this way. If I was over here, it would flop this way. But the secret for estimating means quickly is when you see one of these distributions, pretend in your mind you've cut it out of the wall, that it has a physical weight to it. It's like plywood. Slide your finger along until you hit the balance point And right about in here is where this balance point would be. And you know what, when we calculate the average, it's going to sit right at that balance point. So when you see a distribution and you want to get a feel for where the average is, in your mind, you can pretend that it's been cut out, that it has weight. Where would this thing balance if it were a piece of wood that were cut out? Actually, I expect to see these distributions in yard sales, in you know, all over town. People be cutting distributions out, coloring them, painting them. It's going to be very festive. Christmas time, you see a lot of them. Maybe. In my yard anyway, I'll be cutting them out.